Hello everyone. In this video we are going to study about the BJT applications, feedback amplifiers and oscillators, which is module 4 for the subject basic electronics. Now let us have a look into the textbooks that we are going to refer for this module. The textbooks that we are going to refer for this module are D.P. Kothari, I.J. Nagarat Basic Electronics 2nd edition, McGraw-Hill 2018, and the second textbook that we referred is Thomas L. Floyd Electronic Devices, Pearson Education 9th edition 2012. Now let us have a look into the what is a BJT, what is BJT, what are its applications, and let us study about the feedback amplifiers, various kinds of feedback amplifiers, and also the oscillators. Basically we are going to study about the BJT as an amplifier, and later on we are going to study the BJT as a switch. That is, these are all the kinds of application where we are going to use. So BJT will be used as an amplifier, BJT will be used as a switch, where in which the transistor switch circuit to switch on or off an LED and a lamp in a power circuit using the relay. And later on we'll be studying about the feedback amplifiers, its principal properties and advantages of negative feedback, types of feedback, right? And later on we'll be studying about the voltage series feedback, its gain stability with feedback. And then we'll be studying about the oscillators. In oscillators we'll be studying about the Birkhausen criteria for oscillation, then the different type of oscillators, that is RC phase shift oscillator and the VN bridge oscillator. And we are going to study about the IC555 timer, that is a stable oscillator using IC555 timer. So these are all the things that we are going to glance upon in this module. Now let us have a look into BJT. Now what do you mean by BJT? The bipolar BJT stands for bipolar junction transistor. This bipolar junction transistor, or simply we call it as a BJT, so this is going to have 3 layers, that is either it could be NPN or it could be PNP, that is it is going to consist of 3 layers of semiconductors. That layers are NPN or it could be NPNP, and it is going to consist of 3 terminals and 2 junctions it is going to form, that is semiconductor with the help of a semiconductor device. So when we say it is a 3 terminal, now what are all the 3 terminals? It is emitter, base and collector. So a BJT or a bipolar junction is one, it is going to have, which is going to have 3 layers, 3 terminals and 2 junctions. The 2 junctions are emitter base junction and the collector base junction. The 3 terminals are emitter, base and collector. Now almost in many of the applications these transistors are used for 2 basic functions, that is nothing but one is for the switching application and the other one is for the amplification. So the 2 major applications are switching and amplification. Now when we say it is a bipolar, the name itself suggests it indicates bipolar. The bipolar indicates that there are 2 types of charge carriers involved in the working of a BJT. These 2 charge carriers are, what are all the 2 charge carriers? Whether it could be NPN or PNP. So the 2 charge carriers are holes and electrons, where the holes are positive charge carriers and the electrons are the negative charge carriers, right? So once we study about this, let us have a look into the symbolic representation of NPN transistor and PNP transistor. Now we know our BJTs are of 2 types. One is your NPN and the other one is PNP. Now both functioning is same but differ in terms of biasing, right? So when we bias is nothing but applying a voltage, right? So applying an external voltage is called as biasing. So both of them are going to perform the same operation and the working principle, the construction is same and all, but only thing they are going to differ is with respect to the biasing and the power supply polarity that we are going to connect. In PNP transistor, we have between the two P and N transistor. So in PNP transistor, we have P, N and P. So these are all this is the three layer, and I have the terminal as emitter, base and collector, three terminals. So always between the two P layers, we have a look here. So between the two layers, these two P layers, we have the N-type material sandwiched, where in case of NPN transistor, we have NPN. So P is sandwiched between the two N-type materials. So these two transistors are configured into different types like common emitter, common collector and common base configurations. So when we have a look at this, let us have a symbolic representation of our PNP and NPN transistor. So we have the emitter, base, and the collector. So this is our emitter and this is the collector, and this becomes the base of the NPN transistor. The arrow mark indicates, the arrow mark on the emitter, that is outward arrow mark, indicates it is an NPN transistor. Similarly, I have PNP transistor where you have the emitter and collector or also the base region. We can see the arrow mark is indicated inwards on the emitter terminal. So this indicates it is a PNP transistor. So this is how we represent logically the PNP and NPN transistors. Now let us have a look at the construction and working of NPN transistor. How the working principles are also same, but the only thing that we are going to change in the PNP and NPN transistors are the polarities that we are going to connect to the NPN and PNP transistors. So let us consider an NPN transistor where N semiconductor, we already know the majority charge carriers across the N semiconductor is electrons and P is holes, right? So whenever always we know our no matter whatever might be the kind of transistor, whether it could be an NPN transistor or PNP transistor, always we should remember that the emitter base junction should be forward biased and the collector base junction should be reverse biased in order to make my transistor to work as in order to make my transistor to conduct, right? So when we have a look at this, have a look at the terminals that we have connected to the N terminal. That is, this is my emitter part. The emitter N region is connected to negative source of the external bias or external applied voltage, and the hole is connected to the positive of the external voltage, right? Similarly, when we have the other transistor, we have PNP, that is our collector base junction should be reverse bias. So have a look at this, look at the polarity of this. So hole is connected to, that is my P region is getting connected to the negative terminal and N is connected to the positive terminal. So as a result, I can say my collector base junction is in the reverse bias condition, right? So this is what is the condition to turn on my transistor or to make the transistor to conduct. So always remember, emitter base junction should be forward biased and collector base junction should be reverse biased. So this is the condition. Now whenever we apply the voltage across this, so what is going to happen? We know our electrons and holes have a tendency to move from the N region, that is the holes in the P region have a tendency to move towards the N region, and the electrons in the N region have a tendency to move towards the P region as well as N region, right? So as a result, I can say there is a free movement of electrons which constitutes some amount of current. Then we can say our transistor is going to is going to conduct, right? Similarly, with the reverse bias condition, we know our transistor will not conduct, right? So when it is the condition where our emitter base junction should be always forward biased. So when we look into the input and output characteristics of NPN transistors, when we plot a graph of base current versus VBE, right, base current versus the base emitter voltage, we can see our collector emitter current is going to, when we plot a graph of IB, that is base current versus the base emitter voltage, we can, by keeping our collector emitter voltage as equal to some volt, as equal to some constant, we can say there is an increase in the base current as and when the VBE is increased, correct, as and when the VBE is increased. So when we have, this is the transfer characteristic, and when we have the, when we plot a graph of IC versus IC, that is IC versus VCE, we can see there is an existence of the active region where the device is going to conduct, that is my transistor is going to conduct in the active region, and below that we are going to say that is the cutoff region, right. So these are all the basic characteristic which we have learnt in our lower classes also, right. So about the transistors. Now let us see the application. So far we studied the different types of transistor, what is a BJT, what is BJT, what are all the types of BJT, and again we studied what are the construction and working principle of BJTs. Now let us have a look at the BJT as an amplifier. Okay, that is, my BJT is going to have an application as amplifier. It is going to be, it is going to amplify the output. Now what do you mean by amplification or amplifying? It is nothing but the process of linearly increasing the amplitude of an electrical signal, and is one of the major properties of a transistor, right. So if I take my input as this to some voltage, amplification is a thing where my signal is going to get amplified. Okay, where my signal is going to get amplified, that is, it is going to get increased or it is going to get decreased depending upon the amplification factor that we are going to define, right. So the amplification factor is the one which is going to define the process of amplification, right. Now BJT is also going to exhibit a current gain of almost beta greater than 1. When a BJT is biased in the active region, the base emitter junction has a low resistance due to forward bias, and collector base junction has a high resistance due to reverse bias, right. So wherever we find low resistance, I can say there is a flow of current, right. So as a result, whenever we forward bias the emitter base junction, I can say there is a flow of current across the emitter base junction, and there is for the collector base junction, since there is a high resistance due to the reverse bias condition, I can say there will be no flow of current, right. Similarly, let us have a look at this, how my BJT is going to work as an amplifier. So let me take, so this, whatever the, when we look into the arrow mark that is indicated on the emitter, it shows that this is an PNP transistor. Once this is an PNP transistor, I can say this is what is a circuit we are going to connect. Across the emitter is grounded, and for the base resistance is connected, and for the collector is connected, and we are going to give the power supply to the base of the transistor with the collector resistance and VCC. Now a transistor is a, we already know a transistor is a current controlled device, that is, the collector current is equal to the base current multiplied by, that is, we already know this is a current, that is, transistor is a current controlled device, right, and the collector current that is equal to the base current, that is, we know the collector current is equal to the base current multiplied by the current gain beta, right. So we know, that is, when we write it exponentially, the collector current is equal to the base current multiplied by the gain factor beta, right? Current gain beta. The base current is very small, that is whatever the base current that we are expecting here, that is very small when compared to the collector and emitter current. So as a result, I can have my emitter current, that is this one, is nothing but the combination of base current plus the collector current. And we know our collector current or the emitter current is approximately equal to IC. That is, emitter current is approximately equal to IC. Now, what is happening actually? We are applying a signal here at the input. We are applying a signal. What is the application that we are studying? BJT as an amplifier. So, no matter whatever might be my input, this should see to that my output should get amplified, right? My output should get amplified. So what is going to happen? VCE is my output, right? VCE is my output and VBE is my input, correct? So this is my base to emitter voltage. This is my input and VCE, this whole thing is my output, right? So when we plot a graph or when we look into the waveform, we have whenever my VB, correct, whenever my VBB is given as a sinusoidal input, I can say my VC is getting amplified, right? So I can say it is going to get amplified. Now we know the expressions. An AC voltage Vin is to be amplified is superimposed on the DC bias voltage VBB with the base resistance resistor RB in series, which is shown here. The DC bias voltage VCC, this one, the DC bias voltage VCC is connected to the collector of the collector through the resistance or resistor RC. The input AC voltage Vin produces, or Vin or Vs, whatever, produces an AC base current, that is IB, which results in a much larger AC voltage across RC, which is amplified and inverted version. That is what is shown in the waveform, which is amplified and inverted version of an input voltage, which is as shown here, right? Which is as shown here only, right? So it is inverted and amplified version. Now let us study what is the equivalent, that is AC equivalent circuit for this. Okay, what is the AC equivalent circuit for this? The AC equivalent circuit is nothing but for the AC equivalent circuit we are going to remove the VBB and the VCC, that is DC voltages that we have here. VCC is nothing but my DC voltage and VBB is also nothing but my DC voltage. So for the AC circuit or the AC equivalent circuit, we are going to remove the VBB and VCC. Once we remove that, we know the forward biased base emitter junction exhibits a very low resistance to the AC signal Vs or Vn. This internal AC emitter resistance is designated as R dash, that is Re dash. So this internal resistance, emitter resistance, is designated as Re dash. Now we know our IE is approximately equal to IC is approximately equal to VB by Re dash. VB by Re dash. The AC collector voltage is VC is equal to IC into RC, which is approximately equal to IE into RC, and VB is equal to Vin minus IB into RB. Considering VB and VC as transistor AC input voltage and AC output voltage respectively, the voltage gain, that is the ratio of VC to VB, is given by AV is equal to gain is VC by VB. Output voltage is the collector voltage and input voltage is the VB. Now our AV, that is the gain, is equal to AVC by VB. VC is IE into RC and VB is IE into RE dash. When we substitute it, we get the voltage gain as AV is equal to RC by RE dash, right? Since RC is very much greater than RE dash, the output voltage is always greater than the input voltage. The output voltage VC is now getting amplified by the version of VB. So this shows that my BJT is going to be used as an amplifier. That is, it is one of the application. That is, my BJT is going to the application of the BJT is nothing but it is going to act as an amplifier, right? So it is going to get amplified. Now, with this concept, these are all the following. This is the bibliography which gives you the which gives you an inference where we have collected the materials and all. Thank you. Hope this video is very useful to you. Thank you.